Hello, everyone, and welcome to another session of this course. Let me share my screen. So in the previous sessions, we talked about creating a cryptocurrency. And we actually talked about this idea that we use public keys as identities. So whenever I'm talking about someone's identity or someone's address, what I mean is that I want their public key. And we also talked about transactions and the way that we store them. And we talked about not really having account balances, but only having transactions instead. And we said that every transaction gets a bunch of inputs, which are the outputs of previous transactions, and has a bunch of outputs, which can be later used in future transactions. And we talked a bit about how these payments can work, when a transaction is valid, and things like that. And the last thing that we covered in the last session was this idea of having a centralized ledger. So I just have to mention that this is the centralized ledger that I'm asking about in the second homework that was just announced. So whatever I say today is not part of the homework. So the thing that is covered in the homework is this centralized ledger where anyone could create accounts by just creating public keys and private keys for themselves and do transactions. And the only role of the central bank was to keep track of the history of all these transactions. And we talked about the data structure that we use there. So the idea was that we first create blocks of transactions, and each block is basically a set of transactions, which is saved as a Merkle tree. And then we create a ledger or a chain or a linked list of these blocks using hash pointers. And then the idea was that this is similar to the problem that we had several sessions back when we were making sure that the bank cannot change the history, or if the bank changes the history, everyone will find out. Okay, so this is where we left in the last session, and now I'm going to continue from here. Of course, having a centralized ledger is not great for us because it gives a lot of power to the central bank. And basically what we're saying is that every time it's the central bank that decides which block to form and which block to add to the end of the blockchain. And that's not great because suppose that the central bank doesn't like you, it can just not process any of the transactions that you make. Or maybe the central bank wants to put some extra rules on the transactions and say that in order to do this transaction, you have to do some particular thing. So you have to satisfy, let's say, a rule that was set down by a government or maybe by the bank itself. And we don't want to give the bank this kind of control. And also, if the bank wants, they can just shut down the whole system. They can say, okay, we're no longer adding new blocks, and that's also not great because we have a single point of failure. Or if someone does, let's say, a DDoS attack on the bank and makes the bank disconnected, then that's also a problem because they wouldn't be able to get the transactions and process them anymore. Okay, so the main topic of today, and generally the main topic of this course, is going to be about decentralizing this system and making sure that no one has more power than anyone else, so that we don't have a central bank and all users are equal. But for now, what I want to do is to actually do the opposite and give some more powers to the central bank. And just before giving these powers, I have to mention that the central ledger that I mentioned in homework 2 is the one without these extra powers. So I'm just talking about how we can make it even worse. How can we make it even more centralized? So one thing we can do here is that we can say no one can transact without the bank's permission. So for example, we can say that every transaction must be signed by the bank. Okay, this is one level more control given to the bank in comparison to here, where anyone could make a transaction, and as long as it had the right signatures, it could be sent to the bank and put into the chain. So now we can give the bank even more power and say that every transaction must be signed by the bank. Or another power that we can give to the bank is that we can say the bank can print money. So the bank can create new units of currency. What would this look like? Well, it basically means that the bank can create transactions. So let's call it the transaction of the bank, such that the sum of inputs is strictly less than the sum of outputs. Okay. If we give such a power to the bank, then that's effectively like printing money. The bank can create new units of currency. Okay, what else can we do? Well, actually, it turns out if the bank has these powers, there's not really any more power you can give to the bank. The bank can do anything with these powers. So suppose that, for example, the bank wants to, let's say, confiscate a coin that belongs to you. What the bank can do is that it can just never sign any transaction that uses that coin, and instead create a coin with that same value by just creating another transaction that has a higher output than its inputs. Okay. Now, why do I even bring this up? Because it seems like this is the exact opposite of what we want. Well, I bring this up because this is what's called a central bank digital currency. And a lot of countries have actually implemented this thing. And they kind of call it a cryptocurrency or a blockchain or something like that. But actually, the kind of control that they have is so massive that it's nothing similar to Bitcoin or Ethereum. So I just wanted to show you that even though this is not great, we can still make it even more centralized, and we can give the bank even more power. And this is actually what's been being implemented in the real world. Okay, but now let's go to our own main topic here, which is how to make it decentralized. So if I want to make the whole thing decentralized, basically what that means is that I don't want to have a central bank, but someone should keep track of the chain, right? Of the chain of blocks, which we call it the blockchain, of course. So who's going to keep track of this chain or this ledger? Well, again, since we don't want any kind of centralization, and since we want everyone to be equal to everyone else, we can just say the answer is everyone. So in a decentralized ledger, we would just say that, well, the data structures are the same, but everyone keeps track, or actually it's better to say can keep track of the ledger. Okay, so we don't have one single source of truth. For example, the bank's ledger that says that anything that I say is true. Anyone has its own, their own copy of the ledger. And well, of course, the problem that happens as soon as you have several copies is how can you make sure that all the copies are the same? So this is what we call a consensus problem. So how to make sure that everyone has the same ledger, or let's say blockchain. So here we are getting rid of the bank, but we still have to keep this data structure, which was our ledger, which is a linked list of blocks. And again, each block is just a Merkle tree of transactions. So what we say instead is that, okay, now that we don't have a central bank, let's everyone keep track of this. But if everyone keeps track of it, then they might have some differences in their copies. And how do we make sure that they get to the same copy? And also, actually, the way I've written it here, it becomes impossible, because if you want to make sure that everyone has the exact same copy of the blockchain, that's impossible, because, well, as a user, I can just create a fake blockchain for myself, right? If it's just stored on my computer, I can change it as I like. So it's not really that we want to make sure that everyone has the same ledger, but we want to say that everyone who follows the protocol, everyone who is honest, so everyone who follows the rules that we put down will get to the same ledger as everyone else who has followed the rules. Okay. I'll come back to the questions a little bit later, sorry. So, well, if everyone has to keep track of everything, then there are several problems that we have to solve. So the first problem is the problem of transactions, or actually let's call it transaction propagation. So how do I send my transactions to everyone? Because originally here I had a central bank, and if I wanted to do a transaction, I would just create my transaction, sign it, make sure it has all the right signatures, and I would send it to this central bank, right? But now there is no central bank. So how am I going to publish the transactions? That's one problem that we have to solve. The other problem that we have to solve is who forms the blocks? Because again, here, when we talked about the idea of blocks, our problem was that we didn't want our chain to become too large. So we didn't want a chain of transactions. We wanted a chain of blocks. But there was never a problem of forming the blocks, because of course the central bank can form them, right? The central bank gets all the transactions, it can put them into blocks as it likes, and there's no rule about that. But now here, the next problem that we will have is who forms the blocks? Okay. What other problem do we have? Well, the other problem that we have is how are the units of currency created in the first place? So I talked about transacting, and I talked about these transactions that should have some inputs and some outputs, but in a sense, this definition is cyclical. In order to create a transaction, you need a previous transaction, right? Because you need the outputs to become inputs of your transaction. So how do we have the first transaction? Like how is money created? And of course, the answer was that here in the centralized world, we could just say, okay, the bank can create new units of currency. So the bank could create a transaction that has, let's say, no inputs at all and just a bunch of outputs. But then when we become decentralized, when everyone is equal, there is also this question that how do we create new units of currency? How do we, let's say, print money? Okay. So as you see, we have several problems, actually 4. So how do we send the transactions around? How do we form the blocks? How do we reach a consensus about the order of the blocks and the chain that we have? And also, how do we create new units of currency? Okay. So let's try to do these things one by one, and let's try to do them from easiest to hardest. So in the first case, I just want to look at this problem. How do we do transaction propagation? Let's call this problem number 1, maybe. So this is easy, right? Because you can just do it the same way that any distributed gossip protocol works. For example, if you've used torrents, that's also probably how torrents work. What you can do is that you can just say, I have a network, and let's say that this is my network, and I have all the nodes that are running, let's say, the Bitcoin protocol. They might be in different countries, and some of them are connected to each other. Okay, maybe the connections are, for example, like this. So this might be, for example, a node that is running in China. This might be a node that is running somewhere in the US. Who knows? There are maybe millions of nodes, maybe thousands of nodes. It depends on the size of your network. But what do I want to ensure? I want to ensure that when I create a transaction and when I sign it correctly and it's a valid transaction, I want to make sure that everyone on the network knows about it. So what I can do is that I can just say, as a user, as the person who is creating the transaction, all you do is that you send your transaction to one of the nodes. And then I put a rule on the nodes and say that as a node, whenever you get a transaction, you just broadcast that transaction to all the other nodes that are connected to you. So if this node receives a transaction, it would just broadcast the transaction to all 3 of its neighbors. Now this one receives the transaction, so it broadcasts it to both of its neighbors. This one might receive the transaction twice, but that's fine. Each node can just keep track of the transactions that they have heard until this point. And if a transaction is repetitive, they just add it to their list only once. Okay. So this one was actually pretty easy, how to propagate the transactions. I should just add one point here, and the point is that the nodes should check that the transaction is valid before passing it, right? Because if I am, let's say, a Bitcoin node and someone gives me a transaction, this person can be a normal person or it can be another node. I have to, at the very least, check that the signatures on this transaction are correct, right? And the transaction is well formed and so on. Because otherwise, I'm just wasting networking resources if I propagate a transaction that is incorrect or invalid. So the propagation part is very easy. Anyone can give the transaction to any of the nodes on the network, and any node on the network would send the transaction to any other node on the network that is connected to it. Okay? And so the idea is that since this is a large network and since everyone is connected around the world, and let's say we're using the internet, after a while, everyone would hear about this particular transaction. Okay. So let me answer your questions and then I'll go to the next problems that we have here. Okay, so one question is, what incentive does the government have by creating blockchain-based central bank digital currencies? Honestly, I don't know why they use blockchain at all. It's just a weird thing. It's like they like the word blockchain, so they prefer to do it using a blockchain. It does give some level of transparency in the sense that, well, you can see the ledger, even though the ledger is controlled by a centralized authority, and you can make sure that the history didn't change or something like that. That's good, but yeah, as we will see, it doesn't give you really the same level of privacy as a decentralized ledger. Yeah, and there are some other comments here that say track everyone's transactions or prevent money laundering. Well, these would not be incentives for governments to do these things because they can do it in the current system, right? So what's the point of switching to a blockchain? And honestly, there is no point. Okay, So the next question is, what if one node received 2 transactions? How does it know which one comes earlier? Okay, we'll have to talk about that. This is actually related to the next problem, how to form the blocks and so on. And the other question is, how long will the propagation last for each transaction? Well, that depends on the network and the speed of the connections and the speed of the nodes. In practice, it usually gets propagated in under a minute right now. But yeah, there is no good way of analyzing it theoretically. So another question is, once the transaction is propagated, does every single node verify the validity of the transaction? Yes. So the idea is that every single node should do this, but again, since anyone can join the network, we don't know which nodes are honest and actually follow the protocol and which nodes are not honest. So when I say every single node verifies the validity, I mean that every honest node does it. Okay. So there is a question about a 51% attack. It's going to come up a little bit later, so I'm just going to skip that one, sorry. Now, going back here, so we know how to do transaction propagation now. But one of the good questions here was that suppose that I am a node, for example, I am this node, and let's say that I received 2 different transactions. How do I know which one came earlier? And the answer is, at the moment, you have no way of knowing. So if you just get 2 transactions, let's say I first received transaction 1 and then I received transaction 2, it might be the case that transaction 1 was really made earlier than transaction 2, or it might be the case that transaction 2 was made earlier, but there was more delay because it was announced to a, let's say, farther point of the network and it took more time for it to reach me. Okay, now this is particularly problematic when you have transactions that are in conflict. For example, transactions that do double spending. So here's an example. Let's say that I had one transaction, let's say transaction 0, and it had a particular output that said, I don't know, give 5 Bitcoins to Alice. So I just write 5 Alice. And let's say that I received this and I agreed that this was a valid transaction as a node in the network. Now let's say that later on I received 2 different transactions and one of them is using this output as its input and sending it, let's say, to Bob. And there is also another transaction, let's call this one transaction 2, that is using the same output as its input, but sending the money to, let's say, Carol. Okay. So as a node who receives these transactions, I have no way of saying which one is valid. I know for sure that at most one of these 2 transactions, transaction 1 and transaction 2, can be valid, but I don't know which one. Because conceptually, the one that came earlier should be valid, but I don't have any way of verifying which one came earlier. Okay? So this is also a problem that we have to solve. And as we will see, we will solve it using the next questions that we have here. Okay? So the next question that we have is, who forms the blocks? And again, remember, our idea was that we want to have a perfectly decentralized currency. So we want everyone to be equal to everyone else. So I cannot say that a particular node can create blocks, but another particular node cannot create blocks. So the answer that I can give to who creates blocks should be that everyone can. Okay? So anyone who is on the network should be able to create new blocks. Okay? But then we get to our main problem, which is the consensus problem. If anyone can create new blocks, maybe one of the nodes creates a particular block and tries to add it to the end of the blockchain, and maybe some other node creates another block. in this case, I will not have a single blockchain, right? I will have two conflicting ideas of what the chain of events are, right? So let's say that this was my blockchain. And at this point, let's say that there are two different nodes that are proposing two different blocks to be added. Okay. If everyone is equal, I have no way of choosing which one of these is valid. I don't know. Maybe I have to go with this one, or maybe I have to go with this one. And actually, these make all the difference. This decision makes all the difference. Why? Because, well, again, I might have two transactions like this that are in conflict with each other. And maybe one of these transactions is in one of these blocks and the other transaction is in the other block. So I have to make sure that everyone on the network agrees about the order of the blocks. And if I can do that, then I would be able to also have consensus about the order of transactions. Because if I have an order on my blocks, then of course in each block I also have an order on transactions because, well, it's a Merkle tree. I can have a left to right order on the leaves. So this gives me an order on transactions overall. Okay. So some of you are asking in the chat whether we can use a timestamp or record the time when making the transaction. And the answer is unfortunately no, because see what happens. Suppose that Alice really wants to cheat. What she can do is that she can create a transaction and pay this 5 units to Bob. And then later on, she can create another transaction, but set the timestamp to be sooner than this one and pay it to Carol. So the problem is that we cannot, even if we have timestamps in our transactions, which we do, we cannot be sure that the timestamps are not forged. We cannot be sure that the timestamps are giving us the right order. For that reason, the only order that we have on our transactions is the order that comes from the blocks. So if I can reach a consensus over what the right order of the blocks has been until now, then I automatically also have a consensus on the right order of transactions, because it's just the order that is inherited from the order of blocks. Okay, so we have to solve this one, the consensus problem. Okay, so how do we solve this consensus problem? And let me just, maybe I should have removed this one. Okay, so let's again visualize what we have. We have a blockchain, and let's say that we already had consensus up to this point, but now after this point, we have more than one competitor for what the next block is going to be. And it's not necessarily two, maybe there are 3 people who have proposed new blocks at the same time, right? So we have to find a protocol where we can decide if 3 people have blocks that they want to add at the same time, who gets to add it. And we have to do this in a way that makes sure the whole network, or at least all the honest participants on the network, reach a consensus. And the answer that Bitcoin has for reaching this kind of consensus is called proof of work. And the idea is this. The idea is that we say, let's have a hard problem. And it can be any hard problem. It should be, of course, a computational problem. So let's have a hard computational problem. And let's say that the first person who solves this problem gets to add the next block. Okay. And let the first person who solves it add the next block. Okay. So if this is the case, what that means is that suppose the whole network agrees on these first 3 blocks that we have here. Okay, so the network, let's say, agrees on this. Everyone is in consensus. And now several different people want to add a new block. So they're now in a kind of competition. And what they have to do is that they have to solve this computational problem as soon as possible. And the first person who can solve this computational problem can announce their solution and their block and say, hey, see, I'm the first person who solved this, so add my block to your consensus. Okay. So sometimes instead of calling it a hard computational problem, we just call it a puzzle. So this whole thing can be just called a puzzle. Okay. Now, what is the problem that we have here? Well, again, we have a problem that maybe it happens that 2 different people can solve the puzzle at the same time. So if I have 2 different people who suddenly solve this puzzle at approximately the same time, because of the network also has some delay, of course, then what happens is that I might get 2 or more blocks, and maybe all of them have solved the puzzle. So what I want to do, ideally, is that I want to make this puzzle so hard that it's unlikely that 2 people solve it at the same time. Okay. And another word that we have here, and I want to define before continuing this, is the word mining. So mining is just solving this puzzle. So whenever I talk about mining or proof of work mining, what I mean is the process of solving whatever hard computational problem we have that we have to solve. Okay, but let me be a bit more concrete and actually tell you what the problem is in Bitcoin. So what are some hard problems that we have seen until this point? So we've seen that, for example, computing discrete logarithms is hard. But at the very beginning of the course, we also saw that inversing hash functions is hard. So the puzzle in Bitcoin is a kind of hash inversion. So the idea is this. Suppose that I have a hash function h, and let's say that I want to add my block to it. Okay, so let's say that I can do it like this. Let's say the last block that I want to add is B. Okay, if I have a block B and I want to add it to the blockchain, of course, this B also has a hash pointer to the previous block, right? And it also has a bunch of transactions in it, right? And we talked about the transactions being basically stored in a Merkle tree. So if I want to actually be even more concrete about it, what does each block contain? It has a hash pointer to the previous block. It has the Merkle root of its transactions, which, as we saw before, basically is a summary or digest of all the transactions that are in this block. So I don't need to put all of them in the block. I can just put the Merkle root. Okay. And yeah, so let's say this is what we have. In Bitcoin, we have a bunch of other things. For example, we can also have a timestamp and so on, but I don't want to talk about that right now. So this is what I have in my block P. Now I want to define a puzzle that includes this block P. So what I can say is that I can say, okay, let's also put a nonce here, which is any number that can be chosen by the person who wants to add this block to the blockchain. Okay. And then I say that I accept this block only if the hash of this block is small. So for example, if the hash of this block is less than some number, I don't know, let's say less than 2 to the power of 128. Okay. So remember that the hashes, especially in case we use SHA-256, or in case of Bitcoin where we use 2 iterations of SHA-256, these hashes are really long. So these hashes are 256 bits, let's say. And if I say that I want you to find me a block such that the hash of this block is at most 2 to the power of 128, that's actually a really hard problem. Because what that means is that I want you to effectively kind of inverse the hash. I want you to find a block such that when I compute the hash of this block, and let's say I'm writing it in binary, it starts with a lot of zeros, right? So I want, for example, the first 128 bits of the hash to be 0, and then the next 128 bits can be anything. Okay. So this is the problem that I want to pose here. So the problem that I want to pose is that I want to say you can add your block B if your block has this particular property. If when I take the hash of your block, the first few digits are just 0, or well, I can then talk about how I choose the number of digits that should be 0, but for now, let's say it's just 128. Okay. So someone asks, what is the function of the nonce? So suppose that I don't have the nonce. If I don't have the nonce, and I just have this block B that consists of a hash pointer and a Merkle root, when I hash the block, I will get a fixed hash, right? And maybe that hash does not have this particular property that I like it to have. But if I also have a nonce, then what I can do is that I can just try different values for this nonce so that I get a block such that it has a small hash. And that's the idea. That's the way that I'm going to solve this puzzle. Because I have to provide a block such that when it is hashed, it gives me a lot of zeros at the beginning. What I do is that first I create my block. I create the hash pointer to the previous block. I create the Merkle root. And then for the nonce, I just start trying random numbers. So maybe I do it sequentially. Maybe I say, okay, my nonce is 0. I compute the hash of this block with nonce 0. And I see if it has the number of zeros that I need. If it doesn't, then I change my nonce. I say, okay, now my nonce is 1. Now again, I do the hash, and so on. So what I have to do in order to solve this problem, in order to find a block such that when I hash it, the hash becomes really small and starts with a lot of zeros, is that I have to just try many different nonces over and over again and just compute the hash with these different nonces. Okay. So another question is, what if the nonce does not exist? We'll talk about that. Actually, that's very unlikely in practice. It's working and it exists most of the time. It depends on how you set your parameters, and I will talk about that. Okay, but before doing that, let's come back and see how this would solve our problem. So let's say that I have 3 different blocks that are already in consensus, so everyone on the network agrees about this. Now, anyone who wants to add a new block should do this kind of hashing that I said here, should try to solve this puzzle, should create this block, and then try different nonces and hash them over and over again until they find a block with the right hash. And that's our hard computational puzzle. Now, it's quite unlikely that several different people on the network can find the hash at the same time, can find a block with the right hash at the same time. So the most likely case here is that maybe only one of them, maybe this guy, can compute a block with the right hash sooner than everyone else. And then when that happens, this guy would just announce this block to the whole network. And the way this announcement works is exactly like the way that we do transaction propagation. So this guy has a new block, and this block, he was lucky or he did a lot of hashing and he could find a block such that the hash of the block is small. So he just announces it to the whole network, and then the network propagates this. And after a while, everyone has heard about this particular block, and everyone knows that this particular block has the right hash. So everyone adds this particular block to the end of their blockchain. And we also have some sort of consensus. I will talk about details of this a bit more. Okay. So I'll talk about some of the questions before coming back there. So now the next problem that we have is what happens if I know it's kind of unlikely, but what happens if two different people solve this hash puzzle at the same time? And by the way, again, solving the puzzle is called mining. So whenever I talk about people who are trying to add new blocks, I call them miners because they're doing mining, of course. So now the problem is what happens if two miners find a solution, find a valid block that should be added at roughly the same time, so that when they announce their blocks to the network, again, as a node in the network, you have a problem similar to this. Instead of getting two transactions and not knowing which one came before which, you might get two valid blocks and not know which one is the earlier one. Okay. So in this case, Bitcoin has a very nice rule. And so the rule of Bitcoin is this. It says that the longest chain is the consensus chain. What does this mean for you as a node on the network? Let's say that you are a node on the network and you have seen a bunch of blocks and you already agree with all of these blocks and you are in consensus with everyone else. And now let's say that suddenly you hear about two different blocks that want to be added to the end of the blockchain. And let's say that all of these blocks have the right hash. Okay. So what you would do is that you would temporarily say, okay, right now I have two different valid blockchains. I have this one, which goes up here. So I have this one. And I also have this one. So as a node, I would temporarily accept both of these as valid. But then later on, as miners continue working, miners are also seeing both of these valid chains, and each miner can choose which valid chain they want to work on. But at some point, someone will add another block to one of these. And as soon as that happens, as soon as one fork becomes longer than the other fork, then the longer fork is the consensus chain. So as soon as we have something like this, I would say that, okay, this is now my blockchain, and I ignore this part. Okay, because the rule is that the longest chain is always the consensus chain. This might take some time. Maybe it happens that I receive a block here and I also receive a block here. Maybe the chain continues. Maybe the chain becomes forked even worse than that. Maybe it becomes like this. right? So I will just keep track of all of these until one of them becomes longer than everyone else. And as soon as I have a chain that is longer than every other chain, I say every other chain is worthless now, and my chain is this. Okay? So now let's analyze this. What does this mean? Well, even if there is some probability that two miners find valid blocks at almost the same time, the probability that the two chains that they create is extended always in tandem is almost zero, right? So at some point, one of the chains will get longer than the other one. And as soon as one of the chains gets longer, every honest participant, every participant that is really following the protocol would just ignore all the other chains and say that the longest chain is the valid chain. Okay. Now I want to go and answer your questions. Okay. One question is that the requirement of the value in the puzzle determines how hard the puzzle is. Yes. So if I say I want 128 bits of zeros here, that's effectively setting a difficulty for this puzzle. If I say I want only 1 0 at the beginning, that's a very easy puzzle. If I say that I want it to be all zeros, that's the hardest possible puzzle, right? Okay, so another question is that, isn't there a possibility that the node that solved the puzzle is a malicious entity? Well, yes, that's possible. But here's the thing. I said that the blocks are propagated in the exact same way that the transactions are propagated. So what does this mean for you as a node? It means that you just keep listening for transactions and for blocks. If you hear a new transaction, as I said, you will just announce it to all of your neighbors, to everyone that is connected to you. But before doing this, before the announcement, you make sure that the transaction is valid. You make sure that it has the right signatures. You do the same thing for blocks. So suppose that this is your blockchain until this point, and let's say that someone wants to add a new block at the end of it, but this block contains an invalid transaction. So if the block contains an invalid transaction, then the whole block is invalid. So if someone sends you a block and you as a node look into it and see, oh, it has a transaction that is invalid, it has a transaction that is doing, for example, double spending, you would just ignore this block, even if it has the right hash. So having the right hash is not the only condition, it's just one of many conditions. So let's actually talk about this. Let's talk about when a block is valid. So when is a block valid? Okay. And this is actually the check that you will do as a node when you receive a new block that you want to add to your blockchain. So you have your blockchain, and basically you treat your current version of the blockchain as the truth. So you say, this is the chain of all the blocks that I already know contain valid transactions, and I already know this is the valid history of everything that has happened on the network. Now, someone wants to add a new block. So what do you check for this new block B? Well, you first check that hash of B is small enough, right? So you take the hash and you make sure that the hash is really small enough so that the person who wanted to add B actually has solved the puzzle and the hard computational problem that they had to solve. The second thing that you would check is that every transaction in B is valid. If you have a transaction in B that is invalid, then the whole block B is invalid. So what does that mean? Again, for a transaction to be valid, we talked about this before. It should have the right signatures. It should not create any new units of currency. We cannot create money out of thin air, and it shouldn't do any double spending. So any output that is used in the current transaction as an input should not have been used before anywhere on the blockchain. Okay, so you check these things, and only if both of them hold, then you say, okay, this block is valid, and you'll add it to the end of your chain. Okay? And of course, as I said before, if you get two valid blocks at roughly the same time, you temporarily just keep track of both until one of the chains becomes longer. And as soon as one chain became longer, you say, this is the consensus chain, I ignore everything else. Okay. So now going back to this question here, what happens if the node that solved the puzzle is malicious? Well, they are malicious, who cares? They can't add invalid transactions. As long as the transactions here are valid, we can be sure that we can add that block to our blockchain no matter who created it. Okay. So another question is, if the algorithms for solving are the same, why can't two people find the answer at the same time? Well, because basically you're searching for this nonce, right? And you will use different algorithms for this. Most people would just try randomly checking different nonces to see which nonce works. So it's kind of unlikely that they find it at the same time. And also the thing here is that the computational power between different participants is different. So if you have a supercomputer, you can compute many hashes in 1 second, many more hashes than I can do, for example, with my laptop. So if I just have a laptop and you have a supercomputer and we want to do this competition against each other, it's very likely that you will be able to find the valid block sooner than us. Okay. So there is another question. Can this prevent transaction conflict? What if a coincidence happens? Or is it so rare to occur? Well, you see, the invariant that we always have, so the property that we always make sure is satisfied, is that the set of transactions that appear in our blockchain and in the order that they appear in our blockchain are valid. So at every point in time, as a node, what do I have? I have a blockchain in mind, which might already be forked and have several different chains that I'm waiting to make sure which one is longer. But I also have a bunch of transactions that are not in the blockchain. I've seen these transactions, but I haven't seen a valid block that contains them. So from my point of view, these transactions have not been processed yet. So the only transactions that have been done are the transactions that are on the blockchain. And on the blockchain, I'm always checking that when I'm adding a new block here, it was valid. Every transaction here was valid with respect to every transaction that came before. So I'm always sure that all the transactions that are actually processed are valid. Okay. So the other question is, what if there are two nodes that receive these three transactions, but the two nodes have different winners? So again, as I said, it will just create a fork. You will have temporarily two different chains, but as soon as one of them becomes longer, that's the consensus chain. So someone else asks, so the fundamental reason why mining even exists is to prevent confusion in transaction propagation. In a sense, yes. The main reason why we have this mining is because we want to have a consensus about the chain. We want everyone to eventually have the same blockchain, so that then we can have a consensus about transactions and who owns what. Okay. So someone else asked, how is the authenticity of the transactions in the block that's computed proof of work successfully tested? It's just the normal testing of transactions. So again, if when you get this block, it has a Merkle root, and you also know all the hashes of transactions and so on, so you can know which transactions are here. So when you do the propagation, you actually propagate both the block and all the transactions and the Merkle tree in it. But what ends up in the blockchain is only the block, not the Merkle tree. So you will only have the root of the Merkle tree in your blockchain, but every node is getting all the transactions and all the Merkle trees and all the information that they need to verify that all transactions here are valid. Okay. Someone asked, what happens to the other branches? They're lost, yes. So if we have several branches, like this, for example, and let's say this one became longer, so this whole thing is invalid and we don't care about it anymore. We only care about the longest chain. So someone else asks, all the in these blocks, are all the information other than the nonce the same? Not necessarily. So suppose that you are a minor node, you are a node that receives transactions and wants to create this block. And let's say that I am another node that wants to do the same thing. It might be the case that we have received different transactions. So maybe there is a particular transaction that you are aware of, but I'm not aware of. So if I create the block, I will not put that transaction in, but if you create it, maybe you will put it in. So it might be that the blocks are different, not only in their nonces, but also in their transactions. And actually, this is a good example here. So suppose that I have two transactions that are doing a double spending. So Alice is using this output twice. So what happens? As a minor node, I will see both of these transactions. And I might choose to say that, okay, transaction 1 is valid from my point of view. I want to put transaction 1 in my block. And maybe you are another miner who is creating another block and you choose to put transaction 2 in your block. So effectively what happens is that at the end of the day, one of these two transactions will go on the blockchain, but not both, because at the end of the day, we will reach consensus about the order of blocks, and the chain that we reach consensus on only has valid transactions. So the consensus chain will only have one of these two transactions, but not both. Okay. Okay, another question is that, does this mean that some miners are just doing useless work for some amount of time? Yes, unfortunately, that might happen. So it is very possible that you can, for example, create a block here, and maybe someone else creates a block at the same time as you, and maybe their chain gets longer than your chain. So all of your effort there is wasted, and this block just doesn't make it to the blockchain. So someone else says, is valid and mined the same thing? Well, you can define it as you like, but the way I define valid is this, that it should solve the proof of work problem, it should solve the puzzle, and every transaction in it should also be valid. But generally, you can mine an invalid block, right? So if you create a block, for example, that has invalid transactions in it, you can still mine it technically. You can solve this problem for it and make sure that the hash is small, but it wouldn't be valid. So maybe there is a difference between mined and valid. Okay. So someone else asks what the criteria for a valid block. Okay. So you see, for a block to be valid, what should happen? Well, first of all, we want to make sure that every transaction in the block is valid. So this is point 2. But we also want to make sure that the person who wanted to add this block, the miner who wanted to add this block, should have solved the problem that we said here, the puzzle, which was having a small hash. So we want to make sure that the hash of this block is small, right? And the idea was that when you are making this block, you can choose the nonce. So you can just try different nonces until the hash becomes small. And that's the hard computational problem that you have to do. You have to continually try different nonces. And so it's really hard to find a block that is valid, to find a block that has the right nonce such that the hash becomes small. But actually, after someone finds it and announces it to the network, it's really easy to check that this is a valid block because you just check its hash and check every transaction in it. Okay, so there is another question about what happens if two different blocks are announced at the same time. As I said, we'll just wait to see which chain gets longer, and the longer chain is the valid chain. So another question is, what prevents miners from creating empty blocks? Nothing. Miners can create empty blocks if they like to. But as we will see later on, there are some incentives that kind of disincentivizes them from doing this. But there is nothing in the protocol that says you cannot have empty blocks. So as a miner, you can just create an empty block. Another question is, if there are no transactions, do the miners still continue mining? That's not very realistic. In practice, people are doing transactions all the time. But yeah, I guess even if there are no transactions, the miners will continue mining and will continue adding empty blocks. Someone else asks, miners can modify transactions in the block freely? Well, they cannot modify the transactions because the transactions have to be valid. And in order for the transaction to be valid, it should have the right signatures from the owners of all the monies that are used in that transaction. But what they can do is that they can choose which transactions to put into their block. So if I am a miner and I've received 1,000 transactions and maybe my block has room for only 100 transactions, then I get to choose which ones I put in. Okay. Okay, so another question is, just to check, a person can engage in a transaction, but it's the miners that help to validate these activities, solving the puzzle and help grow the transaction tree, and in turn they earn Bitcoin, right? So I will talk about the incentives for why miners do this in a second. But yes, generally everyone is equal on this network. So everyone can create transactions and announce it on the network. And everyone can also do mining, which means creating blocks and trying to solve this proof of work problem, and also announce their blocks if they find a valid block. So another question is, which chain gets longer in case of conflict? Is it just a matter of luck, or can miners determine that? It is mostly a matter of luck, but it also has to do with the computational power of the miners. And this is actually something that we will cover in detail. So again, just to look at it very naively, let's say that we have only 2 miners, okay? And they compete for creating new blocks. Then if one miner has 10 times as much computational power as the other miner, which means if one miner can compute 10 times as many hashes as the other miner in 1 second, then this miner will be able to add new blocks 10 times as often, right? So your chance as a miner for adding the next block is proportional to the computational power that you're using for generating these nonces and computing these hashes. Okay. So another question is how to determine whether the hash is small enough or is it relative to other blocks hashes. So I'll talk about that as well. So for now, I just said that, let's say we've set a particular number of zeros that we want to have at the beginning of our hash, but I will talk about how we choose that. For now, let's just assume that it is chosen. And another question is, does a miner need to restart the computation if another miner announces a block faster? Yes, because as soon as another miner block announces a block, it's very likely that the block that you already had now has a bunch of repetitive transactions or maybe a bunch of invalid transactions. So what you have to do is that you have to create a new block and start fresh, basically. Okay, another question is, since the block is only valid if every transaction in the block is valid anyway, why design such rules that only those who solve the puzzle can add the block? Well, because let's go back and see how we checked when a block is valid, right? Sorry, when a transaction is valid. So the idea was that a transaction is valid if it satisfies 3 requirements. The first requirement was that it should have the right signatures, and you can easily check this. The second requirement was that it shouldn't create any new units of currency. The sum of inputs should be larger or equal the sum of outputs. And this is also something that we can easily check. But if you look at the third one, it says that you shouldn't be able to do double spending. So what it says is that if you're using a previous coin in this transaction, you have to make sure that no previous transaction has used the same coin. But this only makes sense if you can have an order on your transactions, if you can say which transactions are before this particular transaction. So whether a transaction is valid or not depends on the order of transactions. And this is also what we had here. So if in the order of transactions, when we're doing a double spending like this, if transaction 1 comes first, then transaction 1 is valid and transaction 2 is invalid. But if in the order of transactions, transaction 2 comes first, then transaction 2 is valid. But we can't have a consensus over the order of transactions. So different people on the network might have different ideas about that. So the way we reach consensus is by doing this mining, by adding these blocks. So again, here, when I want to check whether a block is valid, why do I have an agreed upon sequence of previous blocks? Because I have done this process and we have all reached consensus on the previous blocks. So when I add this block, I can make sure that I'm only checking the transactions in the previous blocks to make sure that the transactions here are valid. Okay. Another question is, where are the transactions stored before they're included in the block? Well, any node can store the transactions in any way that they like. So what's included in the block is actually just the Merkle root of the transaction. So the details are just things that the nodes can save on their own. We don't really care about how they save it, because the things that we need for consensus is just the information that we already have in the blocks and the blockchain. So we just need an ordering of the blocks and the Merkle root of transactions. And as we saw before, this uniquely determines the transactions. And of course, you have to save those transactions independently. Okay. So another question is that eventually the nodes will have to store a large amount of data. Will this be a problem? This is true, and it is a problem, and Bitcoin doesn't really solve it. So if you want to store all the transactions and all the blocks and everything in Bitcoin, it will take a lot of space. So another question is, why should the puzzle be a super hard computation? Can we have an easier puzzle? Well, if you have an easier puzzle, it's more likely that people would solve it at the same time. And we want to make that as unlikely as possible so that people don't solve it at the same time, and so that eventually we get a chain that is longer than all the other chains. Okay. Now, let me go back and fill in some of the details here. So one of the details is, how do we set this number? Like, how do we say how small should the hash be? And the answer to that is that different currencies have different ways of doing this. In Bitcoin, generally, what we do is that we also include a timestamp in this block. So we will also have a timestamp. And of course, as I said before, the timestamps can be forged. So we don't really rely on the timestamps that much. But the idea is that using the timestamps, we can figure out how many blocks we are creating and at what speed. And what Bitcoin does is that it says the rule is that we want to have on average 1 block every 10 minutes. Okay. So if I want to have 1 block every 10 minutes, what I can do is that I can say in the protocol at every 100 blocks, or maybe, I don't know, at every 200 blocks, whatever, just look at the timestamps and see how long it took for the previous, let's say, 200 blocks to be mined. And if the amount of time that it took for the previous 200 blocks to be mined was so that we had more than 1 block every 10 minutes, then I will increase the difficulty, which means that I will decrease the bounds that I have here and say that I need to have more zeros. On the other hand, if I looked at the 200 previous blocks and I saw that on average they took less than 10 minutes each, then I increased it, and then I decreased the difficulty, which means that I increased this number. So I can easily set the difficulty so that I have 1 block every 10 minutes, or this is in case of Bitcoin. In other currencies, it might be a different time. But what I can do is that I can just look at the history of the last 100, 200, whatever number of blocks, and based on that, set the difficulty so that I can have on average 1 block every fixed amount of time, every 10 minutes, for example. So that's how Bitcoin does it, how these things are set. And again, since everyone is in consensus about the order of the blocks and the blockchain, so everyone is also in consensus about the timestamps that they see on these blocks. So everyone can just look at the 100 last blocks in the blockchain and figure out if they have to change the difficulty. And it's generally just a formula that is written in the Bitcoin paper, and they use that to set the difficulty here. So another question is that, has this worked historically well? Like, did the difficulty work well historically? The adjustments, yes. So generally, a block is mined roughly every 10 minutes. So sometimes it becomes 9 minutes, sometimes it becomes 15 minutes. So it's not very exact, but roughly it's the same. You will get a block roughly every 10 minutes. Okay, but now we get to a different problem that I also want to talk about today, and that's the problem of incentives. So I just talked about what the miners should do in order to add a new block. And this wasn't easy at all. Basically, in order to add a block, you have to just do this repetitive, really useless computation where you just change the nonce and repetitively compute the hash, right? And this is an expensive thing to do. So you will need hardware to do this. And you will also need a lot of electricity, because it's not free to do computation. And of course, it's not free to do so much computation. So we have to somehow pay the miners for their efforts. Otherwise, no one will do the mining. And since no one will do the mining, we will not have a blockchain at all. So we need to have some incentives for the miners to actually do this. And here's the idea. So we had another problem up here that we didn't really answer. And the problem was, how do we create new units of currency? And now here we have a problem of how do we incentivize the miners to actually do mining? So we can mix these two things together and say that every time a miner adds a valid block to the blockchain, we just pay them some fixed amount as a reward for being able to do the mining so fast and so nice. So we will have a block reward. And the idea is that it compensates the miners for their efforts, for doing all of this proof of work, which wasn't easy or cheap at all. And it also creates new units of currency. Okay, so we kind of solve both problems with just one solution. And so the idea here is that in every block, the miner can include a specific type of transaction. And this transaction doesn't have any inputs. It only has one output that pays the block reward to the miner. And this is how we create new units of currency and also how we pay the miners. So let me just write it here. Each block has a special transaction with no input that pays the reward to the miner. And of course, paying the reward means that it sends the reward to the public key of the miner. Okay? And everyone on the network will accept that every block has one such transaction. Okay? So this is how we can do both things at the same time. Now we can be sure that the miners will do the mining, and we can be sure that we have a way of creating new units of currency. And in Bitcoin, generally, the block reward was 50 Bitcoins at the beginning, but at some predetermined intervals, it gets halved. So it became 25 Bitcoins, then it became 12 and a half, and now I think it's 6.25 Bitcoins every time you mine a new block. And generally, it gets it keeps getting halved as we go on. So very soon the block rewards will become smaller and smaller, and this also makes sure that we will not have too much inflation. So the total number of units of currency that are created is bounded, so we will not have infinitely many Bitcoins. Okay, but here's a problem with this kind of incentive. The problem that we have is that we have now incentivized the miners to do the mining and create blocks, but they can just create empty blocks, right? There is nothing in this system that assures that the miners will have some incentive in order to put transactions into their blocks, because the block reward is a fixed number, right? You get, let's say, 12 and a half or 6.25 Bitcoins every time you successfully mine a block. But, well, if that's the case, as a miner, why should you even bother looking at the transactions? Why should you even put transactions in your block? You can always just have the empty Merkle tree here and just look for the nonce, right? So this is the reason why we have another type of incentive for the miners. And this other type of incentive is called transaction fees. Okay. So remember that I said before, when I was talking about valid transactions, that a transaction is valid when the sum of inputs is larger than or equal to the sum of outputs. And this was something that sounded weird at the time. Like some of you asked, why isn't it equal? Why shouldn't the sum of inputs be equal to the sum of outputs? And basically the reason is that the difference would be the transaction fee. And this difference will be paid to the miner. So if a miner, if a miner puts some transaction into some block and mines this block, or let's say adds this block B to the blockchain, then the miner is paid the transaction fee, which is the sum, the sum of the inputs in this transaction minus the sum of the outputs. Okay, So whenever you create a transaction, you have to think about this. You have to think about how much transaction fee you want to pay. And basically the way you pay transaction fees is that you set the sum of your outputs to be smaller than the sum of inputs. And you know that any difference will be paid to the miner. Okay. And generally, if you have an urgent transaction that you want to go into the very first block that comes out, a good way of making sure that your transaction will be there is to pay a large transaction fee. So the more you pay in transaction fees, the more incentivized the miner is to put your transaction into the block and mine it. Okay. Okay. Yeah, so this is a whole overview of Bitcoin, and this was all I wanted to say for today. So this is the end of today's session. You can leave now. I will remain and answer some questions. So just to give you an overview, what this means is that you have many nodes on the network. Every node listens for transactions and listens for blocks. And when they receive these transactions and blocks, they verify that they are valid. And if they are valid, they propagate them to their neighbors. Some nodes are doing mining, which is this process of solving this puzzle in order to add new blocks. And there is a competition, of course, and we said that the longest chain is the valid chain. And this takes a lot of effort. Solving the problem takes a lot of effort. So we give some incentives to the miners to do this. And the way that we give incentives is that we give a block reward, which is paid directly to the miner and also creates new units of currency. And we also have transaction fees, which incentivize the miners to put transactions into their blocks. Okay. So now going to your question. One question is, how does every node know that we should increase or decrease the difficulty? Well, generally, we can just set a rule in our blockchain, and we can say that we change the difficulty, for example, every 1,000 blocks. So every node knows that as soon as they get a block whose index is a multiple of 1,000, they now have to change the difficulty. And we also set a formula for how to change the difficulty, which says, look at the previous blocks, maybe look at the previous 100 blocks, and see on average how much time it took for these blocks to be created. And if the average was less than 10 minutes, then increase the difficulty. If the average was more than 10 minutes, decrease the difficulty. And of course, we will have a fixed formula for increasing and decreasing so that we are sure that everyone works with the same difficulty. And the idea is that if you have a rule like that, because everyone is reaching a consensus about the blockchain, everyone also reaches a consensus about the difficulty for the next block. Okay. Is there any group chat for this course? I haven't created one, but you can create it. And I think someone is putting a link here. Another question is, if only the root of a Merkle tree is included in the block, does that mean data for actual transactions are only stored in one of the nodes? Well, data for the actual transactions and actually all the details of the Merkle tree are propagated, right? So any node can choose if they want to keep that data or not, but in practice, a lot of the nodes just keep all of this data. Okay. So another question is, the input and output we just discussed were the amount of money in one single transaction or kind of a bunch of transactions from many different people. So the miner can put any number of transactions in the block, but the idea is that for each transaction, he will be paid a transaction fee. And the transaction fee is the sum of inputs minus the sum of outputs in that particular transaction. So the money that came in the transaction minus the money that went out. So any change will be paid to the miner. Let's say it like that.
Sorry, Professor.
Yes.
Does it mean that every transaction that there is a miner that needs to help the transaction to get in the chain?
Yes. So the transaction is valid only when it's, the transaction is done or processed only when it is in the chain. So if you have a transaction that's not on the chain, no one cares about it.
But doesn't it mean that it takes a large amount of time for every transactions?
Yes, we will talk about this, I think, in the next session. But yeah, generally, it will take at least 10 minutes for it to be mined and added. But then there is the possibility that you have a fork and then this block gets deleted. So you have to wait a long time before you're sure that the transaction is really stable.
But a block could be multiple transactions at a time, right?
Yes.
Oh, so, but is it possible that only that there is only one person that has the most computing power that dominates the chain?
Yes, and that's actually that has happened, I think, back in 2014, if I'm correct. There was a mining pool that had more than 50%, and that's disastrous because they will basically have the possibility to rewrite the whole blockchain.
Oh, okay, I understand.
And yeah, we will talk about this attack also in later sessions. Okay. So another question, suppose there is a transaction on a shorter chain and the transaction is already done, so the coin is already transferred, then the shorter chain is ignored. Does the coin in the shorter chain get lost even if the transaction already happened? So this is the conceptual problem. The transaction has only happened if the transaction is in the consensus chain. So if you have a chain like this, and let's say you had another block here, and let's say you had a transaction inside this block and this block got ignored, that basically means that this transaction is also ignored. So it's as if that transaction never happened. So the only way you can be sure that your transaction has happened is to wait for it to come into the blockchain and wait for it to be part of the longest chain. And we will talk about this probably in the next session. Okay, great. So there is a question about how the actual transactions are propagated. I'm a bit confused how other nodes will know the overall content of a Merkle tree. So there are 2 points here. First of all, well, the transactions are propagated and the blocks are propagated, so everyone knows about those. But then you can propagate the Merkle tree itself so that everyone knows all the parts. Everyone knows the Merkle tree, all the transactions and so on. But generally, that's a bit too much for some of the nodes. So some of the nodes in the network prefer to only keep track of the blockchain itself and not of all the extra data that there is. But in practice, all of this data is propagated and everyone has access to all of this data, okay? It's just not put on the blockchain. And the reason is that we want to keep our blockchain as small as possible because we want to reach consensus on the blockchain, okay? But the idea is that as soon as you have consensus on the blockchain, as soon as you have consensus on the Merkle root, it's effectively the same as having consensus on all of the transactions because no one can change the transactions without changing the Merkle root. So it's enough for us to only have the Merkle root in the blockchain here. So another question is, if someone else sends you some cryptocurrency, you can't use it unless it becomes part of the consensus chain. Yes, that's correct. Well, you can create the transactions if you like, but it's a very risky proposition. So you have to wait and make sure that the transaction is actually on the consensus chain and the chain is long enough that it's unlikely that you will have another longer chain later on that erases this transaction. Okay, great. So any other questions? I'll stop the recording now.